Next, we're going to solve this problem using Lagrangian mechanics. So what we have here is a wedge of mass capital M that is resting on a horizontal surface, but can move without friction horizontally. And then we have another block of mass M that can slide without friction also along the hypotenuse of this wedge. And our job here is to find the acceleration of this block relative to the wedge. That is, how fast does the block accelerate down the wedge relative to the starting point up here. If we were to solve this using just Newton's second law, it would actually be a relatively involved problem. We have a wedge, and we have a block, and they have positions in x and in y. And we would have to know what the normal forces are here at both of these two interfaces. And it is actually not the case that the normal force at this interface cancels gravity on this block, because the wedge will be accelerating backwards, and the direction of the acceleration of this block here is not going to be there for purely down the wedge. It's going to be at a steeper slope downward because of that. So we will have 4 equations from Newton's second law. And then we have another 2 equations that relate the accelerations of the 2 blocks. We'll have a total of 6 equations that we would need to solve simultaneously. One of them we can get rid of pretty quickly because the motion of the wedge is in only 1 dimension, but we have 5 equations. We have to make sure all that gets done correctly. And it's easy to make a mistake. As you'll see, things here are a bit simpler if we use Lagrangian mechanics. So let's follow our recipe here for solving this problem. So first of all, we need to make sure that the non-constrained forces have a potential. Well, there's no friction. Friction is a non-constrained force, and it doesn't have a potential associated with it, but we've said that there is no friction. Now, as it turns out, friction is one of the things that is actually relatively simple to deal with within the Lagrangian framework. It's just that we haven't done it, and maybe we'll leave that for a homework problem or something. But for now, we don't know how to deal with the friction, but no matter, there is none. And the only other potential here is the gravitational potential. So U gravity is mgy. Okay, so that was simple. Choose the generalized coordinates. Well, there are several ways you can do that. Given that we are interested in finding the acceleration relative to the wedge, a natural choice of a generalized coordinate would be the distance down the wedge like this. So I'm going to call that Q1. And here's, by the way, another way in which Lagrangian method is superior. In the method I just mentioned, using just Newton's second law, we will get the accelerations in terms of the x and y positions of the of this block. And then we would have to, or both blocks, and we would have to take those 3 variables, those 3 kinetic variables, and turn that into the acceleration in Q1, which is more algebra. Here, this will come out completely naturally without us having to do anything in particular. Okay, so that's one variable that we're interested in, one generalized coordinates. The other one should probably be the position of the wedge here along the x-axis. So I'm going to call that one Q2. Now, part of this step here is actually to relate the generalized coordinates to other coordinates that you might have, and to see how many degrees of freedom you have thanks to the constraints. So we have here 2 objects, and each of them can move in x and y. So we can say that the position of the wedge, we're going to use capital X and capital Y to describe that. And we have the position of the block, that's x and y. So we have basically 4 unconstrained coordinates. At the same time, we have 2 generalized coordinates. Q1 and Q2. So with 4 unconstrained coordinates and 2 generalized coordinates corresponding to 2 degrees of freedom, that's what it looks like here, right? We will need 2 constraints, and those are going to be the fact that the wedge can only move on this horizontal surface and that the block can only move on the wedge. Those will be the 2 constraints. So it seems like we have the right number of variables here. So 4 Cartesian coordinates, 2 constraint gives us 2 generalized coordinates, so it's holonomic. Okay, next step now is to write down the kinetic energy and the potential energy. And there's one thing here that we have to make sure that we follow, and that is that we do this in inertial coordinates. Now, warning, Q1 is not inertial. Okay, if you were to write down the kinetic energy directly in Q1 dot, odds that we would get it right because of that are pretty slim. So what I'm going to do is just dumbly write down the kinetic energy without taking into account the fact that there are any constraints of any kind. So first we have the kinetic energy then. That's just going to be the kinetic energy of the wedge plus the kinetic energy of the block. And that's it. I'm not going to take into account anything having to do with the constraints or the generalized coordinates because that will probably just trip me up. Same thing now for the potential energy. Okay, so that's easy enough. The hardest part now is probably to write down the constraints. That is the trickiest part of the problem. So I'm going to do that over here. Constraints. Okay, so there are 2 constraints. There's one that says that the wedge can only move along the horizontal axis. So that constraint is pretty simple. That's just that y equals 0. Capital Y equals 0. So that means, of course, then that y dot equals 0 as well. That's one constraint. The second constraint is that this mass can only move along the hypotenuse of the wedge, and that's a little more complicated. So I'm going to write that one constraint as 2 equations. And what I'm going to do is I'm going to relate the position of this wedge, actually this corner the position of this block, this corner of this block, to Q1. That turns out that will be the simplest way to do that. So let's see now what x might be equal to. X equals, now capital X, that's just the distance from here to there. So little x is big X. And then I have to add in Q1 cosine alpha. Right, that's the distance in the x direction. So distance from there to there is capital X. Distance from there to there is Q1 times cosine of this angle alpha here. Okay. And then we do the same thing for Y. It's just going to be the height h here minus Q1 sine alpha. So some are constraints. There are three equations here, but there are only actually 2 constraints because we're involving this new variable here, Q1, as well. We're including the definition of Q1 in the constraints. We take the time derivative of this, we get a little x dot is capital X dot plus Q1 dot cosine alpha, and correspondingly for Y dot. Okay, so those are the constraints. These are the time derivatives of the constraints. And that's all we need now in order to rewrite the kinetic and the potential energies with its constraints applied and with the variables changed. Now, the next step here is to change the variables and then to apply the constraints. I'm going to do that at the same time because we have sort of already mixed them up. There is one other thing that we need to note though, and that is that capital X and Q2 is the same thing, right? So we could have used Q2 as capital X, but it'll be simpler to keep Q1 and Q2 on the same similar form. So let's start with the kinetic energy. 1/2 m times Q2 dot squared plus 0 squared, because y dot is 0, capital Y dot is. And then we have to put in the square of this, remembering that x dot is the same thing as Q2 dot. So where I've used that Q1 dot squared times cosine squared alpha plus Q1 dot squared sine squared alpha is just equal to Q1 dot squared. Okay. So that's the kinetic energy. Now, just looking at this, we can see that it was probably a good thing that we started out with writing down the kinetic energy in the Cartesian inertial coordinates. I don't know about you, but I would have had a hard time writing down this form just looking at Q1 and Q2 here. Right? This is what comes about. This term here would have been easy to neglect. This is supposed to be Q2, by the way. So Q2 dot squared plus 2Q1 dot Q2 dot cosine alpha plus Q1 dot squared. Not obvious, but if you follow this template, you will get it right. Let's rewrite it one more time here, just to make it a little simpler to calculate, because we have two Q1 dot terms in here. All right, and then we just have the potential. Well, first of all, this is 0 because y is 0. And I'm going to ignore the constant from now on. All right, next step, according to our list here, is write down the Lagrange equations for the remaining coordinates. Well, we went from 4 coordinates, capital X, capital Y, little x, little y, into 2, Q1 and Q2, so there should only be two Lagrange equations, and therefore the Lagrangian should only depend on those two variables and their time derivatives. So that's the Lagrangian. And now we'll just write down the Lagrange equations. Now, when we're dealing with something that's a little more complicated, it's often a good idea to start with writing down the generalized forces and the generalized momenta separately. So we'll start by looking at Q2. So the generalized force here, the LdQ2, is 0. The LdQ2 dot, though, I see I made a mistake here. Over here I changed the Q2 into a Q1. And the reason I discovered that, by the way, is that if that hadn't been the, otherwise there would have been no Q2 in this equation, and we would have had the generalized momentum in the Q2 direction also be 0, and that's just not physical. Okay, so those two are supposed to be equal to one another, well, with a time derivative. With the time derivative applied to the generalized momentum here. Since this is 0, we can just write down that this guy, generalized momentum, has to be constant. And if you look at what this means, well, here we have the velocity Q2 times the mass of the wedge plus the block. And over here we have the x direction, well, the velocity of the block by itself in the x direction times its mass. This is actually just the total momentum of the system in the x direction. So what we have here is conservation of x direction momentum, and that's something you would expect, right? Because the only driving force on the system is gravity. Gravity pulls downward. There's no friction present anywhere, so we would actually expect the momentum in the x direction to be constant, be whatever it was when we started. So that's what we get from Q2. Next, let's look at Q1. The generalized force, partial to L, partial to Q1, is mg sine alpha, and the generalized momentum mq1 dot plus mq2 dot cosine alpha. Now we'll write down the Lagrange equation. Now what we're looking for here is the acceleration in Q1. We wanted Q1 double dot, and that means we have to find an expression for Q2 double dot. So we didn't quite finish over here, so let's do that. So just take this and plug it in over here. And I found another mistake. This cosine here turned into a sine. Since I don't like stacked fractions like this, I'm going to rewrite this on a slightly simpler form. And that should be the answer. Now, we should always be in the habit of checking it. So first of all, we have an acceleration equal to an acceleration times mass divided by mass, so it has the right unit. Let's check a couple of special cases. So first of all, if we take alpha equals 90 degrees, that means that cosine alpha is going to be 0. Excuse me. It's going to be 0. And then we see our first error immediately here. Sine squared alpha. Didn't transfer that. Otherwise this would not have worked out. If we do that, we get q1 double dot equals g times m plus m divided by m plus m. So that's just g. So by setting alpha to 90 degrees, what are we really doing here? Well, we would basically be saying that this wedge is really a vertical wall, and this block would just be falling down, which it should be doing with acceleration alpha, with acceleration g, the acceleration due to gravity. So that's correct. And it helped us catch an error. If we hadn't tried that, I wouldn't have noticed that I actually wrote a cosine there instead of a sine. Let's try a couple other things. We can try the other option here. Alpha equals 0 degrees. Well, then sine of alpha equals 0, and that means that q1 double dot equals 0. That also makes sense. If the wedge becomes flat, there's nothing to accelerate anything. Third thing I'm going to try is m enormously much bigger than little m, which should mean that the wedge is essentially stationary. So in that case, little m can be ignored here, and I would just get that g1 double dot equals m sine alpha divided by m with a g in front. So that's equal to g sine alpha. That also makes sense, right? If the wedge is stationary, if it's fixed, then the block would just slide down with the acceleration that corresponds to the component of the acceleration due to gravity along the plane of the wedge here, and that's going to be just g sine alpha. So that seems to be working too. So odds are this is a good solution, and that's what I'm going to go with. So it looks relatively complicated, but the way we came up with it was actually a fair bit simpler than it would have been if we had applied Newton's second law straight. We didn't have to have 6 coupled equations that we needed to solve.